right, good morning. Not dissecting any sharks today. Okay, so today we will be talking about something that you might find smelly or gross though, which is wastewater treatment. Specifically, we'll take a look at the secondary treatment. We talked a little bit last time about kind of the overview of what a typical wastewater treatment plant would look like, especially kind of for municipal waste. So what we think of as our typical sewage, domestic type stuff. Sometimes you'll have systems like this for industries. I had a chance to tour a tissue recycling plant while I was in Michigan, and they had a wastewater system where they were needing bacteria to eat a lot of the carbonaceous molecules that came out of their tissues that they were recycling. So it'd be like break down cardboard or whatever. Some of that will dissolve or be really fine, less than fiber size particles, as they're trying to extract all the fibrous stuff and then essentially recycle that and put it into kind of recycled paper towels or toilet paper type of products. Well, some of that would escape, and it would be too small to capture in their fiber processing. And so then they needed some sort of a way to digest it. So they'd use microbes, but it was a very different scenario than what we'd have with municipal situations because there was no nitrogen or phosphorus. It was all just primarily carbon type of molecules. So they actually had to fertilize their bacteria in order to have the bacteria to grow, adding ammonia and phosphorus. So kind of one case example there, but they had a similar system so that their bacteria could perform that task. Okay, so typically then for our secondary treatment, what we're after is control and propagation of these bacteria so that we can have a good environment for the bacteria to grow and eat the stuff in the water. So typically what we'll do is we'll put a box control volume around our primary aeration tank. We would also typically call this waste activated sludge, so WAS. We would call the stuff inside of the aeration tank. So activated because it is oxygenated, sludge because it is a sort of a slurry of bacteria and other stuff. And of course it's waste, right? So waste activated sludge, that's often how we would refer to the stuff in there. So our aeration tank, that's doing the primary job. Then the clarifier, this will be the secondary clarifier, right? Because we have some sort of primary treatment on the left where we had some sort of a screen or bar rack, and then a clarifier here that would probably join up like that. I'm going to avoid confusion there and just leave that as a side note. So that would be our primary treatment, and then we have what we would call primary effluent would be the secondary influent. Okay, does that make sense? It's discharging from the primary step and into the secondary. So when we deal with word problems in wastewater, pay attention to effluent versus influent, right? That's going to tell you about where we are in our system. Okay, so once we've done that, we send it to the bacteria to eat a bunch of stuff. We oxygenate it, really trying to drive down the BOD by letting the bacteria grow on the stuff. So they're essentially removing BOD by demanding oxygen that we're giving to them. Then we have the secondary clarifier, which is going to serve as a way to collect just about all of our bacteria. And in terms of the scale of bacteria in these systems, it is actually close to all of it. If we're talking about grams per liter of bacterial mass, and then a tiny bit slips away and through, yes, it's enough that we have to disinfect and everything. We're definitely not truly get everything, but on a mass basis, it's pretty close. So assuming that things are operating properly, we don't have bad bacteria that are going to act funny and float or anything like that. We'll come back to that. But assuming that all works, then we have bacterial recycle to make sure we keep a good, healthy population of bacteria constantly in our system. And then, of course, we're going to send a bunch to waste. So here we would call that the waste activated sludge line. So it's the WAS up there. So now this is the, we've collected and harvested that sludge. And so that's, I guess, perhaps a better description of where it actually is coming from when we condense it down into that true sludge. You could call it this though, WAS as well. It's just less sludge-like in that form. Okay, so in this tank, we have a few things, and we see these letters. You know, a lot of times when we draw a mass balance or draw something up, we identify what's in this tank, and of course, it's going to be well mixed, generally because of the bubbling. So we see the bubbles there, but we have V for volume, pretty typical. We have X and S. So moving forward, we're going to define each of these, but real quick, as a big picture overview, X is going to be our microbes. So the amount of microbes in our system is going to be important. That's going to dictate how much food can be consumed, because you need the microbes to consume them. The number of microbes in there is going to matter. But then the amount of food for them, which would be called S, that's our substrate, is also going to matter. So S is ultimately what we are trying to handle with the whole system. We're trying to reduce that, but we need to manage X at the same time. So then once we send it through the clarifier, as we'll see, this X in the effluent should be pretty small. That way we capture all of the X that we produced into the recycle and into the waste. So we'll get into some more details about all of that, specifically this lecture later and in our next one. But that's kind of the big picture of what's going on with our biological treatment, okay? So really, it's all about the microbes. We need to control them, use them. They're going to eat stuff. This waste-activated sludge is kind of our generic name for, I guess, the stuff during that process. Sometimes we might also call it like a mixed liquor suspended solids. That's one of the terms we'll talk about. But like a mixed liquor, meaning it's a mixture with different stuff in it, the bacteria and other things. So aeration, I mentioned, that's really going to provide enough mixing such that it's pretty much a CSTR whenever we're dealing with a tank like that. Our wastewater strength, as we would call it, if you ever work with people in the field, they'll talk about the strength of it. It's kind of like how strong was the coffee, how concentrated is that wastewater, and so a typical like high strength would be up near 500 milligrams of BOD per liter. So we're measuring that in that BOD per liter. We're going to call this our substrate. So on a carbon basis, we often deal with a system like that where it's just like, well, yeah, we've got a lot of carbon type molecules that are going to supply food and energy for the microbes. That's what we want to get rid of. There is technically an aspect that there's also nitrogen and phosphorus, all that kind of stuff as part of the food, some nutrients that are important. But generally when we're talking about like the net strength of the wastewater and the oxygen demand that results, it's kind of on a carbon basis. So this is like carbon food, sort of. So if you were to measure total organic carbon, you could probably get a decent correlation from that to how much BOD there would be in our solution. Okay, so then a weak wastewater would be something like 50, 60 milligrams per liter of BOD. Anything smaller than that, we're really getting to the point where it's so dilute that it might not even make sense to use a biological process Maybe we do an activated carbon filtration just simply to get rid of some of the organics, something like that. So this would be a typical range for municipal wastewater operation. Okay, then we have another term here, volatile suspended solids, VSS. This is in contrast with some of our other suspended solids metrics, like total suspended solids. So the volatile means what we do is we take a sample of suspended solids, we filter it out and say, okay, any solids that are in solution above this size get caught by our filter, and then we're going to burn it and see how much of that volatilizes. So then since we weigh it before and after, we dry it first, then we weigh it, then we burn it pretty hot and at 50 degrees Celsius, 500, excuse me, and we weigh it again, and that difference there is whatever was able to volatilize. So if we think about that, that should be most of our organic molecules should volatilize at 500 degrees Celsius, especially the biological related organic molecules, right? So they should oxidize, they should be driven off as CO2, maybe nitrogen, other forms. You'll be left with a little bit of ash, perhaps if there was some minerals, but if we think about a bacterial cell, there's really not going to be a whole lot of mineral composition there. Most of it's just organic molecules. So essentially what we measure then, when we take this volatile suspended solids measurement, is we measure a crude estimate of the mass of bacteria. So then we can use that term, the milligrams of VSS per liter, as a mass measurement for our microbes. That works because we're dealing with such high concentrations of microbes, and it really does port reasonably well. If we just had a few microbes per liter, there's no way we would be able to use this unless we're filtering thousands and thousands and thousands of liters. And even then, well, what other organic molecules might be accumulating on our filter that are not microbe related, right? If there's some other stuff in the water. So this really works because we're dealing with such high concentrations of microbes. In a sense, it is a crude estimate for microbe mass. But it works. Works for wastewater. Okay, so that's a handy tool, and that's going to be essentially the type of metric we use then for whenever we're talking about what kind of, when we describe X, like we showed a minute ago, we'll measure that, we'll provide that in milligrams of volatile suspended solids per liter. Okay, so what can we expect from a secondary treatment step? Well, typically we'll operate them such that we get 95 to 98% of BOD removed. So if we start, let's say, with a high strength wastewater, we said something like 500 milligrams of BOD per liter. In the, perhaps that's after primary treatment, maybe it was a little bit higher. We got rid of some of the junk, the primary treatment, and then we go into secondary. That's our process. We can expect then that goes down to something like 50, right? Well, actually 25, right? 25 milligrams BOD per liter. So that puts us down to a pretty good spot. Of course, if you think about the oxygen saturation that is possible in water, which is like 8 to 10 range milligrams per liter, that could still deprive, it would at least deprive that water of oxygen pretty quick once microbes are allowed to consume it. So in that case, starting with a high strength and with a 95%, that may not be enough. However, if you have a large receiving large body of water that's receiving this wastewater, perhaps it is sufficient. You'll want to check, and we'll talk about this in a few lectures. You want to have some understanding about how much dilution is going to happen when you add this to a receiving body of water, how much oxygen is entering that just naturally over time, and some things like that. But kind of gives you a decent picture, I think, of where we're at in comparison to if we were to just bottle it up and see what happens to the oxygen levels. We are much closer to a range where natural oxygen entry into water could handle that, right? Okay, another thing I want to just talk about, I already mentioned that at the start, actually, the example of a tissue manufacturing / recycling plant and the wastewater treatment plant it used in order to manage the carbon from the tissue recycling process. So typical biological life, speaking of dissecting things, if we were to dissect a microbe, we would find that it has some proportion of carbon, nitrogen, and phosphorus, and in a fairly regular ratio. A human body would have a particular ratio like that. And this is the CNP ratio then is used to understand a lot of microbial life and key limiting nutrients in the environment. So for the sake of algae and marine systems, it's called the Redfield ratio, where it's typically about 100 times more carbon than phosphorus, and about somewhere between 5 to 20 times more nitrogen than phosphorus. So if we put phosphorus as a 1, so this would be our P, to understand how much, what the nutrient ratios are. If phosphorus is kind of our baseline, then in order for microbes to grow, they typically need 5 to 20 times more nitrogen than they need phosphorus, and 100 times more carbon. You would see the same thing in growing plants. So how do you ratio your fertilizer? Well, it's based on essentially their needs in terms of how much of their plant materials, of their fruit, whatever they're producing, comprises nitrogen or phosphorus or carbon. Carbon, and plants, of course, are going to get their carbon from the atmosphere. Algae would as well, but you could kind of have some understanding about all of this based on that. So for wastewater microbes, in the case of a tissue recycling plant where they have almost no nitrogen and phosphorus available, you're not going to have much growth, even though there's tons and tons of food there. So you have to supply them with that nitrogen and phosphorus. Okay, so that can be important sometimes. All right, so I have a little video we can take a look at for a kind of a typical wastewater treatment plant. This is what it would perhaps look like. This will show a few, a few aspects here. Okay, I don't think this is in the States, so I think you'll see a sign at some point. Okay, so this, I think, might actually be a clarifier there, so sedimentation basin water flowing through. Looks a little bit calm. I could be wrong, and that could also be some sort of an anaerobic, or not anaerobic, but anoxic, so they're not adding oxygen to it. Process that on the right there. Saw briefly on the left, they'll walk by it again in a moment. Another basin. I think on the right here, I think this is a clarifier of some sort, because it's collecting the water over the top right there. So it's allowing, that might be the primary sedimentation. It's just doing a kind of first rough drafts. Water is, of course, pretty dirty still. It moves along under those grates, as you see, enters this chamber here, and this is a than our activated sludge. So all those bubbles going, oxygenating it to the best it possibly can. And continue walking through. So we have several chambers here. This could be connected, or they could be. In fact, this might actually be one large container. So there's walkways above it. Just depends on how they set it up. By the way, I know it's pretty obvious that you wouldn't want to fall into that, but you really, really wouldn't want to fall into it because you have no buoyancy with all those bubbles, and so you couldn't swim, even if you did fall out. So the protocol, if you ever visit one of these, guardrails are now seeming much more important, is to know, by memory, where the closest ladder is. Because you're going to fall into a waste-activated sludge system. If it wasn't gross enough. Okay, so then this spot, this might be their secondary clarifier there on the left. It's getting some scum layers on the top. It's pretty common, so they're not going to collect straight off the exact top of it, and then we can see possibly a contact chamber there. I'm not sure exactly what that spot is, but I think could be some sort of a contact chlorine dosing chamber. And then basically here's where it's exiting the treatment process, and I think it's that water then is what they're going to discharge to a discharge out. Okay. Could be wrong. Could be another step that they're sending it to, but it seemed to me like that was the last. And you can see visibly, it doesn't look nearly as nasty at that point. It's more like that could be river water, right? So that's there you have it. Okay, so in order to really dig into how bacteria are going to function for us, we need to dig into their growth kinetics. So we've talked a lot about kinetics of various sorts, usually with some sort of a decay reaction in mind, because we often want to remove something. Well, here we're going to have a little bit of both. So we want to grow bacteria in order to remove the waste, right? So we have pretty common to microbial systems what we would call the Monod equation, and this is a reasonable way to find the rate constant for bacterial growth. So bacterial growth in the context of something like a wastewater system, or perhaps when you're culturing them to grow them, the mu here, this is going to be essentially our rate constant. So if we look down here, this is the specific growth rate coefficient in per time units. So that means that's going to be our first order growth rate constant. So what we're looking at then with this Monod equation is a lot like the case when we did flocculation and we had the K for the rate at which, the rate constant that determined how quickly the particles are going to meet each other and therefore reduce the number of particles. And it relied on several other things. Here we have a K, except it's a mu. that relies on several other things. Okay, so that's what we're looking at in terms of an equation here. So this will ultimately go into, we'll call it dx for the amount of bacteria, dt, so some rate of change of x. It's going to be a growth equation that's going to be related to mu and x, right? So that's the type of thing that we're looking at. So we'll come back to that and elaborate and flesh that out properly. But okay, so mu here then is equal to mu max. So there's, for a given bacteria or mixture of bacteria perhaps, we have a maximum specific growth rate that we could ever achieve if we give them everything they could ever want. Sorry. So if we gave them everything they could ever want, they would grow with some specific rate coefficient. That's this mu m. So the maximum specific. So that's when they're super happy bacteria, right? Technical terms here, super happy microbes. All the food they could ever want. Then we have S. I mentioned that earlier. S is our substrate concentration. That's the food. Okay. Have that divided by Ks plus S. Now this is an uppercase K. I'm following our book's nomenclature here, so please pardon the several Ks and all of that, the subscripted S here. I'll try to be careful with my handwriting to make sure I show it, but if nothing else, refer back to this slide to make sure you have everything clear here. And we do have another K to deal with later as well. So uppercase K, low subscript S, this is going to be what we call half velocity constant. This is the amount of food that gets us to the microbes being halfway happy in terms of their rate coefficient, okay? So it's a kind of a weird term, but it's saying, okay, well, how much food is required in order to get them to be growing half as fast as they could? That's what it means. So we're going to take the amount of food for half plus the current amount of food that they actually have. That's the denominator. So the specific growth rate coefficient given current conditions, that's the mu, then is equal to the amount, the specific growth that they could ever achieve times the current amount divided by the current amount plus half of the amount that makes them happy. Okay, so kind of a weird equation, but that's what's been developed. We're not like trying to derive that or anything. Just want to explain the different features, and we'll elaborate a little bit on this half velocity constant. If we were to consider different values of our specific rate constant as on the y-axis, mu, where up at the top we'd have mu max, that mu m here. Of course, we'd have 0 down at the bottom. Then what it would look like, so I'll do is I'll draw a little dashed line here. So if we have some boundary where we never expect to reach more than this maximum specific growth rate coefficient, right? So if we think about how quickly they're going to grow, or rather the rate constant that dictates their growth, that's going to be a function of how much food they have, right? We just saw that a moment ago, and just to remind us, it's a function of how much food they have, which makes sense, right? More food, the more they'll grow. And on top, we have a multiplicative. On the bottom, we have this additive term. So what that means is this shape should be a little bit asymptotic at the end of the day. We should be reaching some sort of a plateau of some sort. So the more food we give them on the x-axis, we've got food going in this direction. We should start at 0 because they're not going to grow if they have no food. And it should look, oops, something like, try that again, maybe, something like this, okay? Then we can take a look and say, well, the half velocity constant, this Ks, This is going to happen when we are at 1/2 mu x, right? So 1/2 mu m is this point, and we can take that out to here and say, oh, that's our value for Ks. That's how we find it. Okay, does that make sense? So I just wanted to kind of explain what that Ks is. We don't actually deal with too much of this stuff in terms of deriving it typically, but that's what it is, and that's why it fits into the this equation here. All right, so if we were to take a typical culture media to grow some bacteria, this is a lot like what we do for wastewater generally, in terms of just we're causing microbes to grow, right? But sometimes we'll take it in a lab and say, okay, we're giving you a flask, we're going to mix you up, give you a nice temperature to grow at. We can learn something about bacterial growth just by watching what happens in that culture container, right? So if we take a look at, on the y-axis here, this is the log of x, meaning on a log scale, the amount of culturable bacteria we have. So log scale, this would probably be like something like, I guess it's in the x terms that we could call it that VSS per liter. Or we might say, if we're counting them directly, this might be colony forming units per milliliter perhaps. And we might have like 0, 10, 100, and so on, right? We could think of it kind of like that, where we get up to millions and tens of millions and so on. Time here, we would typically see a system like this in probably hours, where maybe the first 18, 24 hours, we get growth. At some point, the growth levels off. So let me start at the start, actually. So early on, you put some bacteria in the solution, and they've got lots of food. They're pretty happy. What's going to happen is they're like, oh, wow, new environment. What's going on? Okay, sensing some food around me. Maybe I'll start trying some of that, make sure that's good for me. And then there'll be some bacterial signaling and stuff. So we end up with a lag phase before they really start growing and multiplying. Probably 2 to 3 hours before they say, oh, okay, this is a nice happy place, we can start growing. This is why if you were to take, I don't know, like a Sunday picnic and you have a bunch of mayonnaise-filled stuff that, might have a little bit of egg in it, raw egg or something, and you let it sit there for hours and hours. First couple hours is probably totally fine. If it was cold and you just put it out on the picnic table and you get to it within an hour, probably okay. Got that lag phase happening. Give it 4 or 5 hours, then maybe you've gotten to a point where suddenly you're ramping up and you're now 6 hours into the picnic. It's been in the warm environment there with nice mayonnaise filled whatever, nice nutrients, all that. You're suddenly hundreds, if not thousands of times more bacteria than you had a few hours ago, right? So kind of a food safety thing here is consider that lag phase is, a few hours out is probably okay. And maybe if you had food out, left it out for an hour, put it back in the fridge, did that a couple times, you're probably okay, but you don't want to do that every single day because eventually they're gonna start growing, right? Okay, anyhow, so once they hit that acceleration phase, they'll be in this growth phase for probably the next, basically overnight is often how we incubate bacteria in a lab. So they'll probably be growing in this growth phase, happily eating all that food for something like 24 hours. We'll just call that 24 hours. At some point, they'll reach a spot where the bacteria are partly just dying off. That happens, but partly they're also nutrient limited. So they're no longer they no longer have infinite access to food relative to the amount of bacteria that are there. So we're going to hit this plateau, the stationary phase, and essentially they are now growing as fast as they are dying, right? So if we were to take a look at the net growth rates and net decay rates here, they should be equal. Whereas this would be, we had a very large growth rate. Of course, some are probably dying, but it's just kind of small, right? Eventually we'll get to a death phase where maybe there's a few bacteria still growing, being the little cannibals that they are, eating all the microbe residue that they can find because it's still food. So there'll be some growth, but mostly they're dying off, and the culture will be in a decay phase. And if you look at this, even though they're dying off right here, we still have quite a lot of bacteria there. So it's not like there's no viable bacteria whatsoever. It's just the population is declining. Okay, so in such a case, here on the right, we have a few factors going into it. We can see X naught, so the initial amount of bacteria per milliliter in this case, CFU per milliliter. We have some substrate concentration, milligrams BOD per liter. We could isolate this and make this like a proper BOD bottle to check how much BOD there is, and say, okay, well, we start with some amount of oxygen, or maybe we just leave it open to the environment and let it mix and get as much oxygen as it can. Then we can observe, as they show here, during this time, substrate will be decreasing. So we have a DSDT, substrate, that food is being consumed. It is being actively removed by the bacteria growing, and dx to t is increasing up until they're kind of running out of food. Okay, so those are the two rates then that we can consider is a growth rate for the bacteria and a corresponding death or decay rather rate for the substrate. So we'll map those out a little more clearly and give ourselves some formulas to work with those in the next lecture. Today we'll take a look at how some of them are playing a part within a typical mass balance for an activated sludge system. Okay, so mentioned this already, but our growth rate dx dt is going to be mu x. We could call that Rg as opposed to R of x. Just to be a little more clear, we could say R growth here. That's mu x. And we can then substitute the mu for the equation, that Monod equation, and say, okay, well, mu x is equal to, we just took the x out here. We could put the x here if we wanted, but we just put it out front. So we said x times that stuff we had in the Monod equation, right? So we just took this guy and put it in there. So that's our growth equation, x times mu max s divided by ks plus s. So that gives us a rate at which the bacteria will grow. As we can see, that substrate concentration will be changing over time, so that's going to get a little bit complicated. So that's going to be a challenge. Fortunately, there's some ways we can simplify a bit. So then we have a substrate utilization rate. That's going to be the rate at which substrate goes away. Substrate is consumed. And this is going to depend on what we would call a yield coefficient. So if you think about, as a bacteria, you're trying to make more bacteria, trying to gain mass. Maybe you're a weightlifter who wants to get a lot of mass. You're thinking about, okay, how much muscle mass can I yield out of my protein shake, right? It's some yield of mass of bacteria per food that they're eating. And this is going to be some sort of a innate characteristic of the bacteria, probably of the food itself. So what we're going to describe as this yield coefficient then that we need in order to correlate the bacterial growth to the food consumption. That's like the key relationship between them, right? What we're going to define that as, this uppercase Y, is we're going to say it's related to the mu max and a k here. This is a lowercase k. This is not equal to the ks. Okay, so mu k, it's a lowercase k. I'll try to keep this one lowercase anytime I use it. And this is the maximum specific substrate utilization rate coefficient. Okay, so if that is the substrate utilization rate coefficient, whereas mu max is the specific growth rate coefficient, essentially we have a comparison there, right? We have the maximum specific substrate utilization compared to the maximum specific growth rate. That's how we're defining this y. So actually, perhaps I should rewrite this and say y would be equal to this mu max divided by the lowercase k. So that's the maximum specific growth rate divided by the maximum specific substrate utilization rate. The yield coefficient units here are going to be milligrams VSS per milligrams BOD, and I think, oh no, that's fine. Okay, that means that the K has to have units that counteract the per time units of this guy, and then also are the inverse of this. So that gives us, did I write that right? K, I think perhaps I think I did something wrong. Hang on. Oh, I think I have something backwards here. Let me know if you see what's happening. If K is mgVSS per milligrams per liter, milligrams BOD per time, Y should be basically 1 over that without time. I'll come back to this and clear it up. I think I just need to check which way the book has it. It might become clear in the notes in a minute anyway. I'll clear this up. Sorry about that. The equations should hold true. The units will ultimately make sense once we get them sorted out. So with this, we can say that our rate of substrate utilization, based on this yield coefficient, we can connect that with the growth rate. So we can connect the rate at which we're using the food to the rate at which the bacteria are growing, given this yield coefficient. So that's going to simply be our SU, so that's substrate utilization, what did they use? Okay, so that's substrate utilization rate is equal to negative of the growth rate. So, because it's inverse, right? So we're consuming the food whereas we're growing the bacteria, divided by that yield coefficient. Okay, remembering that R of G is mu x, then we have 2 equations so far, and really we're only missing one to get our full understanding of this system. So we now have something to understand the rate at which substrate's being utilized. We know the growth of dx dt, but we also have to have some form of death, right? We need to understand how quickly these are dying off. So R of D then is the last topic, and that's going to be, we're going to have yet another K, but this one's it's a lowercase k with a subscript D for death or decay. So our death and decay rate constant, it's per time, so it's going to be first order, depends on how many bacteria are there. They'll be dying off. And this is pretty straightforward. R of D is negative KDX. That's going to be a pretty standard value based on the type of bacteria. It's not going to depend on a whole lot else. Maybe it would be temperature dependent or something like that. But generally, we can use some constant for that. And that would be a kind of a lookup table type of thing. Okay, so then with that, we get a net growth rate. We could use the net growth rate to say at some point, are we growing? Is our net growth positive or negative for the bacteria? And that would be pretty handy. So this R prime of G, so that net growth rate, net change in X, we can define simply as the growth plus the decay. Makes sense. That's, we add up the rates and that's what we get. However, what we can do here is potentially simplify a little bit by putting the growth rate in terms of substrate utilization. So then we can take this equation that would depend on X in a couple of different ways and then rewrite it so that we get rid of the dependence on X, at least in one case. So we can rewrite growth as negative RSU, so substrate utilization times Y, and say then that rate of growth, the R prime of G, is equal to that negative Y RSU minus KDX. Okay, so that brings us to an example problem I want to cover. This one's fairly involved. So what I would like for us to do is for you to take a couple minutes to think about it, to draw it up, and consider how you would approach it. Just sort of brainstorm, right? If you feel like you've got some way to tackle it, absolutely feel free to do so. At least try to start on the mass balance that would be required, okay? I'm not going to have you solve the whole problem, so we'll go through it certainly, but just give yourself a few minutes. I'll read it and everything to contemplate it, okay? I'll probably put up some equations as well, but I want you to do that in order to hopefully help you see where we have to go with this type of problem. Make the solution a little more, hopefully it will make some more sense. Okay, so what we're given essentially is, in the book, we have this table, 6.7, before we even get started with the problem. And it says we have a typical microkinetic parameters for the K, which this was the, and here's the units. I'm sorry, I confused them earlier. I'll double check. That's milligrams BOD per milligrams VSS per day. Typical range for that would be somewhere between 2 and 10. We'll use a default value of 5 here as a, for the problem. Mu max in per day would be somewhere between 1 and 10. Again, they give us a default value. Uppercase KS. Essentially, we're going to use these default values, but it's just providing some ranges here. So then Y, we get a default value of 0.6, and KD a default value of 0.06. Okay, so the example says we have a shallow pond here in this figure 6.14. It stays well mixed due to the wind and the steady flow of a small creek. So we have a pond, and essentially what we're asking for, it has a little more text in the actual problem, but really what we want to know is X final and S final. So we're just simply what we'll do is in part A, actually, if I were to move forward, here's the problem. I'll come back to that in a moment. So essentially what it's going to ask for is what is the microbe population leaving the pond, what is the substrate population leaving the pond, and we know that we should have X and S in here, and I'll add X as well in some volume. It's going to be well mixed, so this is essentially a CSTR. And we have some input parameters. Okay. So the problem states if the microbes in the pond consume inflowing biodegradable organic matter according to typical kinetics, determine A, the BOD leaving the pond. So for A, we're looking at SF. B, the biodegradable matter removal efficiency of the pond. So efficiency. And C, the concentration of volatile suspended solids leaving the pond. So that would be X. Okay, so we'll go ahead and state here that the first little bit of the solution here, I'll go ahead and give you. The pond can be modeled as a steady state CSTR because it's well mixed. We'll assume the stream flow has been steady for some time, so it's steady state. So first it's saying set up a mass balance on the microbial population, or excuse me, microbial mass, using that pond as the control volume. And it goes ahead and gives you that first start of it. So I'll leave you on this page in a second. I'm going to go ahead and let you digest this for a moment. I'll just rewrite it up here. Okay, so take a few minutes. I guess I gave you a bit of a start already, but see what you can do with that, and I'll get back with you in a few minutes to work through that. All right, so I'm going to go ahead and work with you from here. So essentially, the problem is a bit counterintuitive. So we have an issue where we need to find S and X, but they're both changing, right? So we really need something to let us simplify and prevent us from getting to a point where we're trying to solve for two things that are both changing simultaneously. So when we take a look at the mass balance, the counterintuitive part is that since they rely on one another, we can get a situation, given that our mass balance happens to be the steady state mass balance with CSDR, where we can say that we can get one of these to cancel out. Okay, and so when we do that, first of all, we're starting here, and we're going to start with a mass balance on X, which, I mean, might be clear given that the book started us here, right? It told us, okay, we're going to first set up a mass balance on microbial mass. It didn't really explain that, but the reason essentially is that we can actually get in this particular system, doesn't work for every system. In fact, it's not going to work when we go to real recycle wastewater systems. We have some other simplification tools for that. But if we were to just take a look at what's happening in this pond, well, it turns out that X naught is 0, first of all. So we see if there's not really a meaningful bacterial population to begin with, then this becomes 0 equals 0 minus QX plus this V R prime G. So this R prime of G, let's remind ourselves, is going to be equal to, let's see where I put this. This will be X times mu and I'll write this out. So instead of mu, we're going to put mu s times s divided by ks, the uppercase one, plus s. So that's the rg, right? That's rg here, minus rd, which is going to be x times that kd. Okay, so if that's r prime of g, then we have over here v times, I'm actually just going to go ahead and extract out the x there and say vx times mu max times s divided by uppercase ks plus s minus kd. Okay, so we have that so far. We can add qx to both sides. So we have qx equals x times all that, u max s ks over plus s. And we can see here that we can divide both sides by x, and the x just magically disappears, which is wonderful. So we can, and I'm missing a v here, so we could also divide both sides by v, and that gives us q over v is theta. So we could say theta equals mu max s divided by ks plus s minus kd. So now we have a term where essentially there's no x, and we have a function of s. So now we can solve for s, which is not the most convenient thing to do, but take some algebra, we can do it. So we'll say mu max s is going to be equal to, I'll go ahead and add the kd, so it'll be theta plus kd, and then what I'll do is multiply that ks plus s across. Now on the right side, we need to multiply through to get the s terms by themselves. So we'll say mu max s is equal to theta ks plus, what I'll do is I'll do that way. So then I'll do kd times ks plus s times kd plus s times theta. Okay, that's just multiplying those out. Now, here we have three terms now with s in them, so I'll get them all on the same side. We'll say, it's not going to let me write. Well, probably fit it. So we'll say mu max s minus skd minus s theta equals theta k uppercase ks plus kd. And we need to simplify further. So we can extract that s out and say that's going to be mu max minus kd minus theta, all of that equal to theta ks plus kd.
What did you do to ks and kd?
Ks coming from right here to here. Yeah. Thank you. Yes, perfect. Thank you. All right, so then we can finally solve and say s is going to be equal to, we can go ahead and extract that ks out, I suppose. Ks times theta plus kd Let's see if we did all this algebra right when we take a look back. Divided by mu max minus KD minus theta. Okay. I think I might have done something funny with my theta. Is this the same? Okay, I think this might be the same form. The way I derived it last time, which is probably what I should have followed, has it slightly different. Which I know the way I should have been following from my notes is the right way, because that's what the book gets. So I'm sorry, I was trying to just do it by hand and I forgot to even look. But what I'll say real quick is I think this could also simplify, and maybe you can see if I did something wrong, to be Ks times 1 plus theta Kd. Maybe this is, let's see, what is this doing? Divided by theta mu max minus 1 minus theta Kd. And I feel like this is just dividing by a theta or something. Let's see. I pretended that theta is Q over V. Theta is V over Q. That's what happened. Sorry. So this was not correct. All right. Essentially, so the mistake I made just now, I divided this by V and said that this goes to 1 and this goes to theta. That's wrong. Because theta is V over Q, not Q over V. So let me leave that V here. What that should have said is 1 over theta then. It would have been true as 1 over theta, right? So if we put 1 over theta there, and this is 1 over theta here. So basically we'd have to invert everything. So why don't I just quickly, this process, I just did some algebra wrong, right? So that's all that happened. I'm gonna redo the algebra real quick, copying it so that it's nice and neat. And I apologize, but I'd rather do that than keep all this here. So we're just going to do that. At the point where we had got it to that mass balance and we realized that x's will cancel, essentially from there it is just algebra, right? And it's just a matter of knowing that, hey, we need to solve for s. It can get a little bit involved. But ultimately we should arrive at a value for s, and we just don't want to make this mistake that I made, right? So we're going to say 1 over theta is that. And in fact, what I'll do is instead I'll divide everything by q and say I'll divide everything by qx here, and so that's 1 equals theta times that minus theta times kd, because what we had extracted out that v. So perhaps to make it a little more consistent here, what I'll do is I'll say this times theta. Okay, that fixes it in terms of what I did wrong. From here, and actually I think the solution is a little more straightforward, or maybe I just skipped stuff last time. So we can say 1 plus theta KD is equal to theta times mu max S divided by KS plus S. Okay, yeah, I think I just skipped stuff last time. So we'll have to do the same S separation. Maybe I should have left it, I don't know. That same process, multiplying it out. So from here, we would solve for S. I'll start that process here. Ks plus S times 1 plus theta Kd equals theta mu max S. Multiply across like we did. And I'll skip ahead so that we can finish here. So S should be equal to Ks times 1 plus theta Kd divided by theta times mu max minus 1 minus theta times Kd. Okay, so I'm actually even going to go ahead and give you this equation with the caveat that this is specifically for a CSTR that has 0 inflowing x. Okay, so when you see this on your equation sheet, which I'll try to update soon if I've not already, that way you have it to study from. I meant to give it to you earlier last time, but that's specifically for a CSTR with no x input. Okay, that's only case where this works. So I don't mean to trick you by putting it on there, but I also, if I decide to ask you a pond type question, I want you to be able to not go through all this, because as you see, it's convoluted. But it should make sense, right? There's a trick in the sense that x drops out of the equation given this certain situation. Then we have a solution for S that requires some algebra. Okay. Had I done the theta equation right, this algebra would have been fine. Okay, so then if we put in the numbers, because we get those numbers from the defaults from that table we mentioned a minute ago, take these default values. I would give you those on an exam. Then we can get an S that is equal to, it comes out to 6.9 milligrams BOD per liter. And then we can answer part B as the efficiency. Well, we're coming in at 95 milligrams BOD per liter. And so we're going to take our efficiency, just simply the, we can say that's S naught minus S divided by S naught times 100%. So 95 minus 6.9 divided by 95 should be 92.7%. Okay, so that's part B. Part C then, now that we know our substrate concentration, we can solve for X. But again, this is a little bit counterintuitive because now we have to do a mass balance on the substrate itself. So here we do mass balance on S. I'll start that. We have 3 minutes here, so maybe I'll just pick up here next time. But I'll just write out the first step here. This would be 0 equals Q S naught minus Q S, and in this case plus this substrate utilization rate, which is technically going to be a negative, right? Well, I'll write it as V RSU and then V times RSU. So that RSU is going to contain a negative, right? So substrate utilization, we said earlier, was essentially negative RG over Y. y being mu max over this lowercase k. So we can say that we also know that R of g is mu max s divided by ks plus s times x. So we can ultimately get an RSU that's going to be negative and then put it in there. So I'll just finish writing this out. So RSU then should be, so essentially we're going to have negative x times mu max s divided by ks plus s, then divide it by that k, or excuse me, divide it by the dividing it by the y, which is mu max divided by k. So the mu maxes will cancel, and we'll end up with negative x times lowercase k times s divided by uppercase ks plus s. So then that will go into there. So we'll pick up there next time and finish this problem. All right, sorry about the confusion with the theta.